Alright, welcome you guys. Today we'll be talking about quadratic functions and transformations. Now you've already learned quite a bit in Algebra 1 about quadratics and solving quadratics, and we're not going to stop there. We're actually going to go really in depth into this. But with quadratics, we're going to learn how to look at them in real world situations. We're going to be able to determine what's going on with the actual picture and everything, okay? Alright, so without further ado, here's Desmos, our buddy, yay! Okay, so our normal quadratic is, interesting enough, this term quadratic comes from the idea of squaring a circle. Okay, and it was called jeez, now I have to look that up. It's going to bug me. But anyways, it comes from the from squaring a circle. Okay. Alright, and the idea was, could you take a straight edge and a compass and create a square with a certain area and then create a circle with the same area as the square, and it was proven to be impossible because you couldn't do it for every single number. You can do it for certain numbers, but you just can't do it with a straight edge and a compass. And you can't do it for every single number. You can do it for real whole numbers, integers, but you just can't mess around with it because of pi. It just messes with you. Okay. Alright, so taking a look at it, and that's where the squaring comes into play. Like, what does squaring have to do with quadratics? So that long story short, that's where I'm getting. Okay, so real fast, let me sign in. Wow.
Well, hi. Who are you having a appointment with? Hi, Penny. How are you?
Okay, so taking a look at it, this is the vertex form of a quadratic function. It's the parent function of everything. Okay, and if we mess around with it, if you notice a is being multiplied in front, b is being multiplied by the x. We'll talk about this. This isn't going to pop up as much as to what the b does. That's usually in pre-calculus that we talk about this quite a bit. Okay, and so we're not going to talk about the b as much. We're going to talk about the h, the k, and the a. And just like every other function we learned, especially with families of functions, they do the same thing. So a, if we make it larger than 1, it makes the graph appear skinny, whereas if we make it smaller than -1, it makes the graph appear skinny but in the other direction, flipped over the x-axis. Okay. Alright, B changes it a little bit, and what it's doing is actually compressing it horizontally. Okay. Now, if I make it negative, it doesn't appear to do anything out of the ordinary, but I'll explain that it actually does do something. Okay. All right. H, if I make it positive, remember it moves it to the left. If I make it negative, it moves it to the right. Okay. K, if I make it positive, it moves it up. If I make it negative, it moves down. Okay? Alright, so those are the major ones right there. Now, B and H actually do move it. So if I make B2, now if you notice before, if I made B2, if I put a +1 in there, this moved over to -1. Pretty simple. Okay? Now, if I move B to 2, okay, it now moves it to a half. So I need to make H2 in order to move it over to -1. If I make it 3, I need to move H to 3 just to move it over. So B works in accordance with H on the vertical the horizontal translation and the horizontal compression of the parabola. Okay? Alright, so that's pretty easy and simple just to work with. Okay. All right, now as for the actual function, what you guys are going to be seeing, and let me go to the new blade graph. Okay, the thing to consider is what you guys are going to be working with is, okay, is you're going to be looking at some function that looks like this. Okay, something that looks like this. It's a little bit funky. I better make that positive. There we go. Okay. Alright, so if we take a look at the actual graph, if you notice, it's going to be a very sharp parabolic curve. Okay. So if we want to actually fix it, we're going to have to actually look at the y-axis. Let's make the y-axis in step of 50. Let's make this in steps of 1.
Where we're going. And in psychology, we don't have a perfect view. In science, we know a lot of hard facts. In psychology, we know a lot of hard guesses.
Okay. Apparently that's.
I think they started out. I'm not a huge fan of our psychology curriculum, especially psychology is my first love. And so I'm not that impressed with their psych curriculum. I think my supplemental activities make a lot more sense.
X-axis, trying to fix it.
I think introducing the collective unconscious is kind of like a tabula rasa theory by.
Okay, it's not fixing it. All right, let's slow this down. Let's make that. Make this one.
They wanted students to be thinking about that theory and then applying it to themselves. So they chose everyone.
This is actually pretty funky. Okay, for some reason this is just not showing up, so I'll zoom in the best I can. Okay, there we go. Alright, now when you're actually taking a look at this bad boy, you're going to wonder to yourself, okay, what does the x-intercept mean? What does the y-intercept mean? Okay, the y-intercept is the height that it's initially thrown. So when you're looking at this as a projectile motion, it's the height it's actually thrown. Now the x scale is going to be time, the y scale is usually going to be height. So when you're talking about it in parabolic motion, okay, you're going to have to take a look at this and just look at these 3 points. Okay? Alright. Now here's the thing. That's the initial height. So like let's say someone that was 5 feet tall was throwing something up in the air. It would take this motion over time. So here's the thing. Here's how you read this. Okay. This point up here looks like the tallest point, and it is. This is actually the highest point that it will be. Okay, now that's the highest point from the ground. That's not the highest point from the man. So this object technically only went up 7.25 meters, which was 2.25 meters taller than, or feet, 7.25 feet, which is 2 1/4 feet taller than what the man was that threw it, or the woman, whichever one you want to take from it. Okay? Alright? Now the x is going to be the time. So this is time 0, this is time 3 or 0.375, and that's usually measured in seconds in this. Okay? And then it just comes down into the air and it hits the ground at 1.048 seconds. Okay, now it says -0, but just ignore that fact. It's just 0 on here. Okay, alright, so it's just right there, just working with it. Okay, this stuff is just all set up to where you can actually look at the height of the object, how high it goes, what time it got there, and what time it landed, and at what height it was on the ground. Hint, it's 0 when it hits the ground. Alright, now the other x-intercept, don't pay attention to this if it's on the left side of the y-axis, okay? So, because that's negative time, and you can't have negative time, so you have to think about it. Okay, now how long was the object in the air? You could look at the axis, or you could look at the x-coordinate over here, and it was in the air for almost 1.5 seconds. Okay, how high did it go? Well, it went 7¼ feet above the ground, and it only went 2¼ feet above the person. Okay, all right. Now here's another interesting thing. Let's say I had, let me see, let's just put nothing there. Okay. Now if I take a look at this right here, if I change the equation where there is no initial height, let's say we launched it from the ground, and we actually had, let's change that to 20. Okay. Alright, now here's a unique thing. Parabolic flight or parabolic motion is also symmetrical. So the amount of time it takes to go up to the top of the height of the jump is the amount of time it takes to come down. So if you notice, the time from starting to ending is 1¼ seconds. Okay, halfway in between, which is 0.625 seconds, is the exact height it got to its highest, the highest height it could reach, which was 6¼ feet. Okay. All right. So basically, right down the middle, it's symmetrical. It's taking the same amount of time to go up as it is to come back down. Okay. Now remember, this doesn't have to be parabolic motion. You don't have to throw up with an angle to get this type of motion. You just have to model it over time. So time versus height. So the x-axis is the actual time. The y-axis is the actual height. Okay. All right. The amazing thing is that these formulas that are given to you, they're very exact. These formulas are used in baseball all the time to calculate how far a ball is going to travel. I'll tell you right now, the first number is gravity. It's, if you're measuring in feet, it's -16. If you're measuring in meters, it's -9.8. And as you can see, it's a little bit more powerful here, and that's because meters, you know, it just takes more into account. This is the initial velocity of the object, and it's usually positive. If you're throwing down, then it's just going to continue down, so you can start with a negative. The positive or negative right here, the negative right here doesn't connotate that we are repelling the object, it's just connotating down. So the force of gravity is always acting down, and it's always affecting the acceleration. Okay, this one is just positive the other direction. Now if I threw down like this, obviously I'm dealing with an impossible situation. So I need to think about it in terms of possibilities. Okay? Alright. So as you're working on this, this is going to be initial velocity of the object. This is going, and that's usually measured in meters per second. In this case, since we're using meters, it's meters per second. If we were using feet, it would be feet per second. You know, now if I add a number at the end, like I had with the +5, that is the initial height of the object. So in other words, where did I release it from? If someone's throwing something, you probably are going to be dealing with initial height. If you are launching something, you're probably releasing it from ground level. Okay, so that's some important things to take a look at. Now also another thing to look at before we end today, I want you to take a look at the flight path of the ball. So as we get closer and closer to higher, it's slowing down. It's slowing down, and then all of a sudden on the other side, it's going to have speed, 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 and then it's going to travel faster until it hits the ground. So when you initially lift off, you're going to have a great speed going up, then it runs out of fuel, it stops in midair for a split second, and then comes back down. Okay, so you have to understand is that Desmos is going to show you a really cool picture of how quadratic functions work. Alright, thank you guys very much. Have a great day.